This is Tom Dick, and this short video is part of the TI-Focus AP Calculus series. We'll look at the common question number 1 from the AB and BC exams from 2022 to look at using the TI-84 on the topics of accumulation and averages. We were given a function A of t that described the rate at which vehicles were arriving at a toll plaza, where t was measured in hours after 5 a.m. So to start with this problem, let's illustrate a best practice is to get that function into our calculator so that we really only have to enter it once. So I'm going to use y1 to enter the function a of t that we were given, but I'm going to change the independent variable to x since we're in that function environment on the TI. So our function is 450 times the square root of the sine of 0.62 times x. So for us, x is measuring time in hours after 5 a.m. So let's go ahead and take a look at the graph of this function. Now our times don't go past 10 a.m., or for us that would be x equal 5. So I'm going to set my x min and x max to go a little bit beyond the interval from 0 to 5, so negative 1 to 6. Now looking at that function, it looks like it could get as large as 450, and it would never be negative because of the positive square root there. So I'm going to set my y min to negative 50, so we get the horizontal axis in the picture, and my y max to 500. And let's set the tick marks, or our y scale, to 100. Let's take a quick look at our graph, and here's what it looks like. So we're getting something that looks like a one hump of a sine curve in a sense. Now the question A on this problem asked for us just to set up an interval that would give the total number of vehicles arriving at the toll plaza between t equal 1 and t equal 5. So we would want to write down an integral from 1 to 5 a of t dt. That would be the answer to this question. Now, if we actually wanted a value for that interval to be calculated on the 84, we would need to refer to y1, of course, and we'd be integrating with respect to x. So this is the actual value of the integral, which we weren't asked for. However, in part B, we are asked for the average number of vehicles arriving at the toll plaza over that same interval. So we do want that integral value. We're going to divide it by the length of the interval, or 5 minus 1, and that will give us the average value of a of t over that time interval. Now, part C of this problem asked whether this rate a of t was increasing or decreasing at time t equal 1. Now, the tool for answering that question would be the derivative. So I'm going to the math menu and pulling out the n-deriv. For us, since we've stored this as y1 of x, I'm going to differentiate with respect to x, our y1 function. So I'll retrieve the y variable y1, and we're going to evaluate that derivative at the value x equal 1. Now when we calculate that number, we get 148.9472908. Now, we weren't actually asked for that number. We're asked, is the rate increasing or decreasing? Because that derivative is positive, we know that the rate is increasing. Now, in part D of this problem, we're told that if the rate gets to the level of 400 or higher, a line will start to form or accumulate at the toll plaza. So let's go ahead and graph the constant function y2 equals 400 and consider what's going on in the context of this problem. So it looks like that for x equals 0, which x is time for us, to some value between x equal 1 and x equal 2, we're below that level of 400. In other words, the blue graph is below the red graph. Now, starting at that time, let's call it A, between 1 and 2, up till sometime between 3 and 4, the level is at or above 400. And that's where the line is accumulating. And in fact, the integral of the difference of these two functions will give us the number of cars in the line. So that function is what we want to find a maximum number in that line. So we're going to need, our two critical values will be the two intersection points of these two curves. So let's use the intersection functionality. I'll choose the second curve will be our y1 and y2. I'll move my cursor over near that first intersection point, enter that, and there's our intersection. Now if we go back to the calculator screen and ask for x, it will give us that intersection x value. Now I want to go ahead and store that away. Let's store it. It's the value a. That's actually the value referred to in the problem. It's that first time at which the line starts to form. Now we need to go back to this graph and also pick up that value where the blue graph crosses the red line again and the rate falls below the level 400. So again, I'll pull up the intersection functionality, number 5 there under the calculate menu. We'll choose the blue curve as our first curve, y1. We'll choose x second curve, and then we'll move our cursor over near that second intersection point, and then use that as our guess. It'll home in on the intersection point. There it is. And then if we go back to the calculator screen, ask for the value of x. There it is. That's our second intersection point. And let's go ahead and store that as the value b. So I'll take that last answer, store it in b. Once we've done that, we're ready to tackle the question at hand, which is what's the greatest number of vehicles in the line between time A and time 4? Now, the value of the number of vehicles in the line is the integral from that first point A to time x of the difference of y1 and y2. So we're going to create a function y3 that's that integral function. Has a lower limit of a. Our upper limit is variable x. And we're going to use as our integrand the difference of our two functions, y1 minus y2. Remember, y2 is just 400. And then, of course, we'll be integrating with respect to our independent variable, which we're using is x. So I've created this function y3. This is the function that we want to maximize over the closed interval from x equal a to x equal 4. So what I'm going to do is evaluate y3 at the two endpoints of that interval, a and 4, as well as that one critical value which we've already identified as b. Now it should come as no surprise that y3 of a is just equal to 0. We're integrating from a to a. Now I'm going to go up and copy y3 of a and now substitute the value b to find out what's the value of y3 at that critical point x equal b. I've gotten that value, 71.254. And then finally, let's evaluate at the other endpoint, that's y3 of 4. And we find that that value is a bit less than at the critical point b. Now we're asked for a rounded value to the nearest whole number. So our actual final answer here would simply be 71. Well, that concludes our analysis of this question. For more resources like these, please see education.ti.gov.